So in the in the ANSI standard, they have zone distribution area. The slide showed main distribution area. From there you go to horizontal. From horizontal you can go either directly to equipment or you go to the zone. And so the question was, what is a zone? And this is totally optional. Basically you can combine a group of equipment as a zone for whatever reason you want to do. So there is no strict definition of zone, it's just a group. And so for example, if you define this as a zone, a group of equipments, these are the racks, and you can put that all of them as a zone. So you go from some place to the zone distribution area, which is right there, and then from there you go to each of these equipments. So zone distribution area is in the middle, as opposed to you would have come to all of these. So it's very similar to the idea of top of the rack versus end of the rack. It's just that if you have a zone in the middle, then it minimizes some wiring, and then you can go from zone to the equipment much shorter cable. So this is just optional part of that. And then finally, these two slides are new. The thing about the data center equipment, and we had talked about 3 tiers here: the access tier, the aggregation tier, and the core tier. The access is all layer 2. The aggregation is half layer 2 and half layer 3. Core is all layer 3. Right? You see these symbols here. These okay. Now, the thing about so Cisco calls them switches all the way through. Even layer 3 is a layer 3 switch, and there are layer 4, layer 5 switches, right? And Microsoft had called some of them as routers and things like that. There was confusion about all that, right? And so basically now I'm just following the consistent terminology, calling all of them switches and calling by the name access, aggregation, and the core, like in this order. So each access switch connects to aggregation switches connect to the core routers. If you want to call them core routers, connect to the edge routers. So the edge routers are outside. These are the edge routers. They connect to the internet, and the core routers are inside this domain, right? And then aggregation layer is the transition point between L2 and L3. So this is the aggregation layer, is the transition point between L2 and L3. And low latency, high frequency trading markets, so that we talked about, that has, basically as before, the latency is important. Core routers manage the traffic between the aggregation, okay, I missed here, aggregation switches in and out of the data center, okay. So basically that is as before, the core routers manage the traffic between the aggregation switches. If this and all the switches below the aggregation switches form a layer 2 domain, because there is no layer 3 here. This whole thing is one layer 2 domain. Okay, as long as you don't go to a router, everything has one broadcast domain, and it consists of several hundred servers. Most traffic is internal, and the network is the bottleneck, etc. remains as before. All right, so that fixes that one. There was no problem with this. I think we had a problem with this slide, and the problem was, where do you put the appliances? So all these in the data center, you not only have servers and switches, you also have other appliances such as VPN server, intrusion detection, firewall, load balancers, DNS, DHCP server, NTP server, FTP server, radius server, and so on and so forth. So all of these go between the aggregation and the core router, and this picture shows it correctly. All right, aggregation and the core router, and so this is the access, this is the aggregation, and this is the core. In between those, there is these are the devices that actually Cisco sells. This picture came from Cisco, so it has Cisco's model number, but other companies work equally well. The another thing I have done this time, and I will be doing it from now on, is that all the acronyms that are here, they are defined at the end. So there is a list of acronyms. If you see your handout, at the end there is a whole list of acronyms. So for example, radius, we could not remember last time what radius was. and the radius is remote authentication for dial-in users. Okay, server. So basically, radius came from dial-in days when you were dialing into a website or into what they used to call them. You logged into for internet access, and so basically radius server were used, and they still continue to be used. So even when you do right now, radius is used. So all of these acronyms are defined, and so that finishes the last part. Now we were on moving on to where we were before. Let me see. I think we were on one of these two slides. Anybody remembers?
We talked about oversubscription.
Yeah, we talked about oversubscription. Okay. All right. So oversubscription, we already saw that whatever traffic is coming from below, more traffic is coming in and less going out. Right? And the ratio is called oversubscription. So for example, you might have 32 10 gigabit down, only 8 times 10 gigabit up, and that would be 40 up, 320 down. Give you 4-to-1 oversubscription. Core routers are 1 to 240 oversubscribed. In the sense that if you have a core router, they might have 240 servers underneath, 2 tiers down, each of them with 1 gigabit, but the core router has only maybe 1 gigabit out. Alright, so 240 can hit it, but it cannot really serve all of that. So that is basically the reason that you don't really want to go through the core routers as much as you can. If you want to go from one server to the next server, you want to keep them into the same tree, same part of the sub tree, which is same part of the layer 2 tree, as much below, as close to. So basically, you want them to be as close as possible. Now there is a problem with that. So if you have oversubscription, then you cannot just move servers anywhere you want. So you cannot move from here to that part of the data center. That restricts us, right? So there are ways to take care of that problem later on. But right now, from the concept that we have learned in this class, this is a problem. Service trample on each other, and so because of moving across servers is painful, requires reconfiguration of IP addresses and VLAN trunks, and that actually is the problem with IP. IP was not designed with mobility in mind, and so it just indicates the location, and therefore every time you move, you have a new IP address, and that creates a problem. Now people have to figure out how to get to you. With Ethernet, that's not a problem because you keep the same MAC address. Services trample on each other because if there is a bottleneck, then if one service uses more, then the other service get less. That's a problem, right? And so we need to fix that. Poor reliability. Now we have 2 access switches, but if one fails and you are using both, then the over subscription on the other one goes up by a factor of 2. Hopefully you are not using it, then you are losing money anyway, because if you are not using it, you have paid for the 2, but you are using 1. So that's not good either. So we somehow want to be able to use 2 and not overload. Underutilization is that oftentimes we don't use multiple paths, we just use one path. So one thing which is kind of a standard and becoming a standard and is, as we talk about in the next lecture, that we use is ECMP, equal cost multipath. Equal cost multipath means that if somehow the switch knows that there are 2 paths to the destination, left and right, and they are both same cost, then it will try to send 50% of the traffic this way, 50% this way. Okay? And that way you are basically not congesting the shortest path. I mean, actually, the question in this case is there are 2 shortest paths, right? So you're not congesting one shortest path. Everybody understands ECMP? ECMP is equal cost multipath. So equal shortest cost. All right. Now, what do we need in the data center networks? First thing we need is they need to be scalable. Means we need to be able to add more and more and more as we need it. secure. Obviously, you don't want not only outsiders getting in, but also insiders getting to other people's network. For example, if you have a finance department and a marketing department, you don't want marketing people to see the finance data or finance people to see marketing data. Shared, while they have to be able to use the same servers and same networks, the two departments. Standardized, and you don't want to be logged into a particular vendor or one company. And simplified, and you don't want a network which needs lots of experts, so it's simple to manage, right? And so they call it 5 S's: scalable, secure, shared, standardized, and simplified. Now, second thing is converged infrastructure. In the old days, the servers used to use one network and storage used to use another network. And we will talk about that in the lecture after next, actually, what network apps they use. Just for those of you who already know, storage companies or storage devices use SCSI and fiber channel and things like that. Right? When you connect in storage, you don't connect back to Ethernet generally, you connect it to SATA, ATA, things like that, right? Fiber channel. Those are different kinds of networks than Ethernet. And that was a problem. So now we want to really need one network for both, servers and storage. And we want the network to work with both of them. Workload mobility. We need even larger number of servers in a domain. So we need very large domains for virtual machines. Previously we used to have physical servers. Now each physical server now has 10 virtual machines, or maybe 8 cores, 16 cores, and so on and so forth. And so the number of processors is going up, and the number of nodes is going up, and so we need large domains. East-west traffic. In the old days, the traffic was going up and down to the customer, back, customer and back. Now it is going sideways, right, from one server to the next server. So the old networks were not designed for that kind of traffic. So we need to worry about that. For example, Facebook author gave the statistics that your one Facebook request requires 88 cache lookups, 35 database lookups, 392 back RPC calls, and so this is all inside the data center. Okay, you just made one request inside, and so many hundreds of requests went inside, east-west, right? And so the internet traffic times 935. So basically, I think the word here should say intranet traffic, not internet. So the inside the data center traffic was 900 times what went out. If you added the request and response, HTTP request and response, 935 times that went inside the network, intranet. And the storage traffic on the Ethernet also causes problem, because storage doesn't like loss. If you read a disk and it turns out that there is no data, you are going to be in big trouble, right? And while on Ethernet you do it all the time, you lose packets and frames. So Ethernet, if it wants to serve the storage, it has to change. All right. So those are the requirements, and there are more which will come up as we see, but these are the 5 top ones. Any questions about any of these? None? So 4-post architecture at Facebook. So now the one that I showed you before, though that is not the only one kind of architecture, and the big companies are always discovering better things. So Facebook has this architecture which is slightly different than what we saw before. So let's see what it is. It's a 4-post architecture, they call it. And I will, in a minute, it will become clear what is a post. So they have these rack switches. And they have 10 gigabit links going up to cluster switches. You see, each rack switch is connected to each of the 4 cluster switches. Alright? The cluster switches are connected by 4 40 gig uplinks to each of the 4 fat cats, FCs, fat cats. These are real big switches. Alright, 40 gig. 4. So it's not by 2, it's by 4. So now you see fat cat aggregation switches. So these are the aggregation switches for them, and these are access switches in their terminology. So the terminology already changed. Alright. So now there is a 4-to-1 over subscription. Now there is one more thing, these red lines. These cluster switches are connected in a protection ring. What is a protection ring? Protection ring idea came from the telephone companies. So all the telephone networks have a ring-shaped network. And so let's say these are the 4 switches. They will be connected like a ring here which goes clockwise and another ring which goes counterclockwise. These are directional in the sense that this could be fiber which is light is going like this. This could be fiber in which light is going like that. Okay? If something fails, let's say this switch fails, then this switch will realize that this has failed. It will just short circuit this link here. This will realize that it has failed, and now there is a ring which is working. At least the 3 switches are talking to each other. So this is called a protection ring. Okay, and this is very common in the carrier industry. So Facebook uses that. So this one, 4 switches are connected in a 10G by 8 protection ring. So there are 8 fibers going like that. Alright? And so this is that. And the 4 FCs are connected in a 10G by 16 protection rings. There are 16 rings here. Okay? So, now there are no routers so far, you see. Everything is switches. That is one good thing about this, is that anything can move anywhere here. Second thing is, one CSW failure reduces intra-cluster capacity to 75%. So let's say this switch failed and 3/4 is still up. Right? So there is 75% right there. Yeah, go ahead.
What is the H stand for in the H connection rings?
What it stands for?
H. It means
H?
H is, I mean, 10 gigabit is multiplied by 8. I mean a number.
By 8. 8 fibers. Okay, so this one shows by 2. This says 2 fibers. 2 rings. There are 8 rings.
8 rings between every host.
Yeah. Yeah.
Each ring has 2 or just 1? Each ring.
Yeah, right. So the question is, okay. This is something I will have to verify. Is this a dual protection ring or single protection ring? I would tend to call it dual. So that means there are total 2 fibers in it, and it is a dual. So 8 will have 8 fibers, but it could be they have 16 fibers. So I mean, I don't know that part. Okay. So, but anyway, there are 8 protection rings, which generally I would think means that you could have up to 7 failures, and something will still go through. Okay. So this is highly protected 16 times, and this is so on and so forth. So now here 4 CSWs are connected. One CSW failure will reduce by 75%. By the way, all of this is in this paper which is already referred, so you can also read that and see what if it has any sense in it. But the idea is that if you just do 2 at a time, then one switch goes, the capacity goes by 50%, right? Which is not good. So here they have 4, so the capacity goes down by 75%. The capacity goes down by 25%. All right, now you could increase these numbers and put bigger rings, but then there is a trade-off. If you have bigger rings, there are more failures, and the rings will fail more often. So you don't want to put too many in that either. Okay? All right. Now, this is a hard research topic, how to arrange the data center networks. And I did not want to go into the research part of this. I just wanted to keep it because there are so many research papers on this. Actually, I made a list, but then I didn't put it here. And so this is a current research topic. And every time you go to SIGCOMM, which is the leading conference, you will find 1 or 2 papers on this topic itself. But here is the idea. The latest idea was, or not latest, one of the ideas was that we use Clos network. And the Clos network are named after Charles Clos, 1953. He worked for AT&T and came up with this idea. Basically, in those days, all the switches were real switches, something you turn on and off, cross-point switches, right? And so he designed a network which will require the minimum number of cross points. So if you want to do something, you use his network. And so here is the idea. So if you have a 3-stage Clos network, Clos or Clos, actually more like Clos network, is that you call it R, N, and M. You have to, if you have 3 stages, you call it Clos R, N, M. And in this example, I have taken R equal to 2, N is equal to 4, and M equal to 3. So you have R, N by M switches. All right. So in this case, 2 4 by 3 switches. 4 in, 3 out. In the first stage. The second stage has M R by R switches. So there are 3 2 by 2 switches. 2 in, 2 out. And at the end, you have just the opposite of the input. So you have 3 by 4, 2 of them. So you have 8 in this case and 8 out. So this is 8 by 8 switch. And you can calculate how many cross points are there. This one has N by M cross point, this one has R squared, and this one has M by N cross points. Okay, you can add them up, and then you can find out what is the optimal value of R, M, N, and so on and so forth. Everybody understand that? This is a homework actually, so you need to understand this very well. Okay. Now, notice that this is all one-dimensional, one-directional. Everything comes in and gets out, right? So, when this networking people wanted to use this now in today's network, today's network we don't have anything much one-dimensional. Everything is bidirectional. You send it and you get it back. Although inside the wire, you generally send in one direction. For example, in the copper, you send it in this direction, and then another copper wire goes in that direction, or fiber, and so on and so forth. But generally, both input and output are at the same point. Right? So what they did was they folded it up. You draw it on a piece of paper and draw a line in the middle here and then fold it. Okay, you will get this network. Everybody sees how to get from there to here. You draw a line in the middle and fold it. So everything becomes bidirectional. Alright, now in our traditional sense we will call it a 4 by 3 switch because it has we will call it a 7-port switch, not 4 by 3. This is a 7-port switch, because when you buy a switch, it doesn't say this is input, this is output. Everything is input, everything is output. Right? So you have a 7-port switch, and these are 2-port switches. Okay? So this is a folded clause. And this is also called a fat tree, because the person who first invented it designed a tree. And by the way, this doesn't have to be just 3-stage. You can draw a 3-stage clause, or 5-stage clause, or 7-stage clause, or 11-stage clause, and bigger and bigger and bigger. When you fold it, you get a real tree, nice tree. All right, and the capacity, basically is higher and higher toward the root. So that's why it's called fat tree. Fat tree is very thick at the base, and then as the branches come out, they are thinner and thinner and thinner. All right, so that's the fat tree topology. So here is a fat tree example. There are 6 switches which are identical. All these 6 switches are identical. All of them are 36-port switches. And all of them are 1 gigabit ports. And so what we do is we connect 72 servers like this. We take 18 servers and connect to 18 ports on this switch, 18 servers to this port switch, 18, 18, 18. So there are 72 ports which are used up on this side for 72 servers. Then we take the other 18 ports, we give 9 links straight to the 9 of these, another 9 to 9 of these. Okay, on the right side, and similarly for the other ones. So now you see 9 plus 9, 18 plus 18, total 36 ports have been used up here, 36 have been used up here, 36 on every switch have been used up. Everybody understands how do we get these thick lines? There are 9 cables going in the same place. You put in the 9 different ports. All right. So this is a fat tree network, because you can see the capacity here is fatter. All right. Now the interesting thing about this network is the throughput between any 2 servers is 1 gigabit. If you use equal cost multipath, A can talk to this one at 1 gigabit, B can talk simultaneously to this one at 1 gigabit, and C can talk to this one at the same time. They will not trample on each other. Everybody has 1 gigabit, and everybody can use 1 gigabit to talk to anybody else. Obviously, if everybody wanted to talk to me and everybody has 1 gigabit, you will have trouble because I am the bottleneck. But switches are not the bottleneck. You understand? So this one is what they call full bisection bandwidth. Bisection means you cut it any way you want and you get the full capacity. So basically, so this is identical bandwidth at any bisection and you get 1 gigabit. And so this is very good topology. The main problem is though that you used lot of cabling. This is, as you can see right now, you are using basically the cabling complexity goes up very fast on this one. Okay, so if you put money on the cable, then you get full bandwidth. All right, any question about fat tree? Yeah.
How do you make a bisection? Across the core and the...
Right. So one way to make bisection, we just draw a horizontal line. And so here you get 72. Here you get 72. If there was one more, you will get 72. All right. That brings us to the end end of this chapter or this module. 5 key messages. First is that remember those modular data centers that can be sent, basically a truck kind of thing. You can use it for easy assembly and scaling. So you don't have to start with the racks and start filling them up. You can get all the racks and everything else together. Second thing you learned is that there are 3 tiers: access, aggregation, and core. If you wanted to add, then you would know that the access and aggregation are layer 2, aggregation and core is layer 3. Right? Application delivery controller go between the aggregation and the core in the layer 3. And you need large L2 domains. Why you like L2 domains? Because you can move anywhere without any rework. Moving between L3 domain requires a lot more work, so you need large L2 domains. And then there are many topologies. Fat tree topology is used to improve the performance and reliability. Okay. Homework 3. Draw a 3-stage Clos 4-5-3 topology. Alright? And its folded version. Then fold it and show us the folded version. Acronyms are there, all of them, but then there is a reading list, which actually is the same as it was in the slides. I just collected all of them and put them at the end. So you can click them. As I said, these are all clickable. You can download the single slide version from the website, and then you can click on it and you can read them, and you must read them. And then I also did was Wikipedia separately. So these may not be in the main slide set, but if you read these parts of the Wikipedia, you will get all about some of these things. For example, even the Clos network.